Hello everyone, welcome to Rational Science. Why is it rational? Why do we call ourselves rational? Well, because everybody out there is irrational who tries to do physics or science. Why are they irrational? Well, they're irrational because they move concepts around during their physical interpretations. They transfer energy. They vibrate or excite the field. They move a charge. They move a mass. You know, all those are concepts. You can't move concepts around. And then the other reason is that a lot of people, or just about everybody out there, as far as I know, everyone out there, mediates everything with particles, discrete particles. And there is not a single phenomenon of nature that is invisible and intangible that you can explain in a rational manner with particles, with discrete particles. Okay? And here we do it with something else. We have elongated entities, which we propose. Those are the electromagnetic ropes, and those are going to mediate not only light, but gravity. We have what you could call the grand unified theory. It's not a mathematical theory. It's a physical theory. We have light and gravity in one mechanism. Okay? And that's the essence of this channel. Today we're going to talk about these so-called particles that quantum mechanics proposes. In fact, we're not going to talk about the particles. We're going to talk about something else. We're going to talk about the quasi or quasi. I call them the Quasies because I think you got to be crazy to believe them. The Quasi Particles. Okay, so that's what we're the subject matter of today. If you're not interested in Quasies, well, stick around. You might learn something. Stay anyways. Where do we start? Well, we have to distinguish the quasi particles, from what quantum mechanics, I guess, refers to as the real particles, the authentic particles. You know, what's the difference? Well, if you go to the standard model of quantum mechanics, okay, you won't find a single quasi in there. These are crazy too, but I mean, you don't find any of the quasi particles in there, okay? And you say, well, why not? Shouldn't those be in the standard model of elementary particles? I mean, they're particles, right? So you would think they should be in there. Okay? So in order to see what happened here, you know, I want to show you today a little bit of history of how we moved from real particles, when in the old days people really thought in terms of real particles, real balls. Today they're known as classical particles, corpuscles, grains of sand, whatever you want to think of them as, such little beads. And from there we moved to quantum particles, okay, which are those over there essentially. And then from there we move to the quasies. Okay, so we're getting more and more abstract as we go along. So we need to understand what has happened here. Okay, and a good way to start this is to see how we came up with these particles. I mean, where did these particles come from? Okay, and so let me give you a little history on this. Here it is. This is a chronology of particle discoveries. Okay, and the first particle, I think you could say, for invisible, intangible phenomena. Remember, that's what we're looking at here. You know, the sandbox, we know. Sand, you can get a grain of sand in your hand, you can see it, you can touch it, you know what it is. Okay? This is something different. This has to do with modeling, simulating the invisible, intangible world with particles. Okay? And so since those particles are intangible and invisible, well, you know, they say these are particles. It's all mediated with these gazillions of particles that are all around us. And of course, the first particle was the photon. In other words, people even before 500 BC, they started wondering, you know, what is light, especially light? I don't think they had a notion of gravity yet. You know, they took it for granted, you know, things fall to the floor. I don't think anyone studied that at all, okay? Maybe I'm wrong. Okay? But light is something that did concern them, and they said, what is light? And so the first thing that came to their minds is particles, okay? And the particles that they invented in those days, or that they had in mind, came out of the eyes. It was the Superman theory of light. You know, Superman, he's got this X-ray vision. It's not that light comes to his eyes. Light goes from his eyes through the wall and sees the girl next door, okay? That's the way it works. And yeah, for many years you had these people, first the Greeks, okay? And they believed that light came out of the eyes and went to the objects. The farther an object was away, well, the less you could see it, and at some point you couldn't see it any longer, like at the horizon. And so the light rays coming out of your eyes did not reach that far. That was the notion. It would be Alhazen, Hazan, 10th century, and he came up with this notion that after studying light, he said, no, light comes from the objects to the eyes. Okay, so he reverted that direction, but it was still particles. It was all done with particles. That's what they thought it was. And that lasted even until the 17th century when you had all these folks, and there are a whole bunch more. I'm just mentioning probably the most prominent ones, Galileo, Descartes, and Newton. And they believed in particles. Essentially, they didn't see a reason to change that at all. Robert Hooke, we don't have a picture of him because he was a deadly enemy of Newton, and he was also the right-hand man of Robert Boyle. And when Robert Boyle died, Hooke essentially was the caretaker of the Royal Society. And when Hooke died, well, Newton took over. For the first time, he became a member of the Royal Society, and he erased all vestiges of Robert Hooke, including his picture. So we don't have a picture of him today. But Robert Hooke was the guy who came up with the wave in his Micrographia book. I think it was 1665. He's the first one who mentions that light might be comprised of waves. And that was taken up later on by Christian Huygens, who went in there and analyzed it in more detail. But even in the case of waves, when Huygens and all these other people analyzed the wave, they were thinking of this. They were thinking of the ether, and ether was a bunch of particles, and these particles moved up and down, and they created this wave which was supposed to be light. Okay? In contrast, Newton held that it wasn't really light, that the ether was waving. It's that something was traveling through the ether, again, particles, and they were traveling straight. So it was a question of straightness versus undulating. That's essentially what the fight between the wave theorists and the particle theorists was. It was straight versus, waving up and down. And again, Newton could not figure out how light could travel other than, in a straight line. Anyways, the photon was particles. Okay, it was essentially the first particle, and even to this day, it continues to be a particle in the eyes of all the mathematicians who vouch for quantum, and in fact for relativity as well, and for string theory. Okay, keep in mind, string theory talks about a line, 1D line. What is a 1D line made of? Well, it's made of zero-dimensional points. Okay, so what is each point made out of? Lines. And what is each line made out of? Points. It just goes on and on and on. Okay, so everybody essentially is dealing with particles. And it turns out that with particles, you cannot explain a single phenomenon of nature which is invisible and intangible, such as gravity, magnetism, or light. Okay, about 400 BC, we have Leucippus and Democritus, and these folks came up with the atomic theory. I don't know if they were the originators, but they're credited with it. And they came up and they said, look, the universe is made of atoms everywhere. Okay. Especially anything that's got matter. They probably thought also that air and everything else was made out of atoms as well. That notion would last for hundreds of years until in 1876 we have this fellow, a German guy. He was a glass maker, and he came up with the cathode rays. Okay, that's what he named them in German. They were translated as cathode rays. But they didn't really know what those cathode rays were. It wasn't until Joseph Thomson, he came up with the notion that the cathode rays were made of electrons, and they called them negative, arbitrarily, I guess. And those electrons, as Thomson would theorize, according to mathematical physics, it's called proof. In rational science, we call it theorize. He was proposing, making an assumption, simulating, and saying that the electron was part of the atom, was a separate part of the atom. You had the atom and you had the electron. Okay, and the way he envisioned that was the plum pudding model, as it's known. He said there's this atom and it's got these negative, I guess you could call it fruits, embedded in it. That was his model. But he did think of the atom as being comprised of these negative pieces that fit into the atom as a separate. In other words, the electron was a separate piece within the atom. Okay. Rutherford would show. I show it as 1919 because that's when he wrote his paper, but he really didn't realize it until like 5 years later that there was this thing he thought it was hydrogen atom, but it was really the proton, what he was thinking of. And he saw it as a particle. He thought that the center of the atom consisted of this main particle, which weighed about 1,800 times more than the electron, and that the electron was a bead that rolled around it. And that notion developed between him and Niels Bohr, a couple others as well. So they came up with this planetary notion of the atom. Now we had a proton particle, electron particle, and on top of that we had still our beloved photon. Okay, so we had these three particles. But it didn't stop there. Pauling, Wolfgang Pauling, what is it, 1930, he came up with a notion of the neutrino. He was probably thinking of the neutron, because there was confusion at the time between the neutrino and the neutron. They had different functions, and he kind of mixed them together, and they said, oh, you proved this, but you were really talking about that sort of thing. Okay? And that wasn't, the neutrino wasn't proven to exist, according to mathematical physics, proof, right, evidence, until many years later, 1956, Cowan and his partner, they allegedly proved the existence of the neutrino. Meanwhile, in 1932, Fermi comes up with the notion of the neutron. I think it was like mid-year. And at the end of that year, Chadwick ran an experiment and proved, again in mathematical terms, proved the existence of the neutron. Okay? Positron, we have the electron, this negative electron. This is a positive electron, otherwise known as the positron. Okay? We don't know what the difference is physically. All we know is this one carries a negative sign, this one carries a positive sign, because that's how they behave. If they're opposite, they attract, that sort of thing. And so that's why they put these labels, mathematical labels, that have no meaning whatsoever in physics, okay, negative and positive. And so in 1930, Dirac came with the notion of his Dirac sea, which the sea which really formed space itself, the vacuum. And the vacuum was made of positive and negative particles that blended together, formed, I guess, nothing in his mind, again known as the Dirac sea. And for that, he created the positron. He theorized the positron. Anderson supposedly discovered it 6 years later. 33, also, Fermi came up with a weak force. He's the guy who theorized about it. That wasn't going to be discovered until 1983, way at the bottom, the W pluses, W minuses, and the Z bosons. Okay, so it took a lot of years to apparently prove their existence to the mathematical community, even though everybody believed in them throughout this whole time. Okay, 35, Yukawa discovers or theorizes the pi meson, and Anderson 1 year later the mu meson. They shortened that to pion and muon. Two particles again of the standard model there. Higgs and about 100 other people. In the 60s, they proposed the Higgs boson, the Higgs field. This notion was arising in the quantum community. Higgs wasn't the only guy. He just got the Nobel for it because I guess he was British, and they gave it also to Englert, another fellow who allegedly discovered it before him. So, you know, all that is just politics out there. There were a lot of others involved there. Anyways, the Higgs, supposedly one of the last particles to be included within the standard model. You will never find the graviton in there and never will. Okay, the graviton has not been discovered and never will be discovered except by virtue of the magic wand. They're going to force fit it in there if anything someday, but they have no way of showing the graviton. Okay? The graviton, for all practical purposes, doesn't exist, never existed, never will exist. Okay, and then we have the quarks. Zweig also said he had it before Gelman, but Gelman got the Nobel Prize, and Zweig was a little ticked off about that. Okay, he wasn't even considered, even though he says he came up with a quark. Politics again, and then the Germans, Deci, they discovered the strong force, the gluon, 78, 79, even though it was, again, theorized a long time ago. And that essentially completes the standard model. So here it is one more time. Okay, let me put it up here. Okay, that's what we have there. And you can see there are no quasies, no quasi-particles in there. All we have is these particles that form part of the standard model. Okay, so how is this any different than the quasies, the quasi-particles, or whatever you want to call them? Well, you heard of Quasimodo. You know, he's this ugly guy who crept up a church, a cathedral, the Notre Dame Cathedral in France, and he fell in love with this beautiful girl. Okay, and he swept her off her feet, in a sense. Here, let me show you what I'm talking about for those of you who don't know the tale. Okay, here it is. Okay, that's Quasi there, and he climbs around. You know, he's gonna save the girl. You know, She was facing the gallows there, and he's going to sweep her off her feet and take her away, save the day. Okay, so yeah, why do I mention this fellow? Well, I mention him because you say, why was he called Quasimodo? Well, it turns out that you might think he's half a man, or maybe like a man, or not quite a man, maybe halfway between man and beast, or whatever. He had this hunchback, he had a, this Ortiz eye or whatever. No, he was named Quasimodo because he was when he was born. Parents realized he was born so ugly, so so out of whack that they decided to turn him over to the church. So they left him in a little basket at the door of the church and left. And they said, let the church worry about this guy. And they did it on Quasimodo Day. They did it, or I think it was the day before. They left him at the door of the church. And here's what Quasimodo means in Latin. Okay, and it's the Sunday. It's the Sunday after Easter. Okay, and it comes from Quasimodo, and the first words of the introit, which is the entrance. Okay, the priest comes into the church. Okay, on that day, and it's this entrance. It's called the Quasimodo Geniti Infantis. Okay, and what does that mean? Well, it means as if a newborn babe. Okay, so you enter the church and you kind of enter as a babe, and that's how Quasimodo entered there. So it means, the important part here is the Quasimodo. Quasimodo means as if. And so they use this quasi or quasi or quasi, again I call it quasi in the case of quantum, as a kind of like. Okay? It's not quite, but almost there. Okay? So in the case of the quasi or quasi particles, we're talking about something that's in the process of becoming a particle. It's not quite a particle. It's trying to make it to be a particle. It's trying to graduate into a particle. Okay? And you might say, well, when did this start, this quasi particles? Was this something recently? Turns out that, we had our first quasi in the 19th century, in the early 19th century. And it was this fellow here, and his name was Russell. He was a shipbuilder, and what he did was one day he was watching how a ship came in. Remember, you're talking about wooden ships. Okay. Ship comes in and docks, but as soon as it kind of slowed down and stopped, he found that the wave that it created continued rolling by. And he was on a horse, and he chased that wave down. He went along the bank of the river and just watched it all the way because it caught his attention. And he found out that this wave just kept rolling along. And he called it a wave of translation and wrote about that. He even built in his garage, he built a little device that created waves and studied waves. Okay? He called them wave of translation. And that wave of translation is going to become, in the 20th century, going to become this soliton. Okay? And that's the first quasi that we have on the books. Okay? And what is a soliton? Well, it's a self-reinforcing wave packet that maintains its shape while it propagates at a constant velocity. And here you have a couple examples. There's more examples of this soliton wave. And it's a fascination with a lot of these mathematicians. They study it. They get equations on this. They study them from every angle. For them, it's a big thing. We have no use for these things in science, in physics. Maybe explaining them, that's where the scientific part stops. But we don't go beyond that. They're nothing more than curiosity. That's it. And that happened in the 19th century, but nobody thought about these quasi-particles, or solitons or whatever, until the 20th century. After the mid-20th century, you have this fellow. He's a Soviet scientist, Soviet mathematical physicist. Okay, he worked on the Soviet bomb, and his name was Lev Landau. 1956, he has to invent the quasi-particle, okay, for the first time. He brings it into the vocabulary. Okay, so what is it? Well, he used it to explain a theoretical model of interacting fermions. Okay, and these quasis describe the normal state of most metals at sufficiently low temperatures. In other words, you're talking about, again, collective motion, and he's going to apply this to liquids and to metals. Okay, And his theory explains why some of the properties of interacting fermion systems are very similar to those of ideal Fermi gas, okay? That is, non-interacting fermions, and why other properties differ. And Landau reasoned that what interactions do is to produce virtual particle-hole pairs. Where did he get that? Well, he got it from Mr. Dirac, yeah, where they were dealing with all these particles and holes and positive and negative coming together and forming this background. And he applied that notion, the same notion that Dirac had for his C. He applied it to solid state. He's applied it to several parts of what they call mechanical and electrical physics. Okay, so what came out of all that? Here's a definition first of quasi, as I call them. Just so you know, I'm repeating this from last time. Quasi-particle is a collective excitation. They're emergent phenomena. When you have many, for example, atoms or molecules or photons or electrons vibrating in a given way, well, they call that collective excitation a quasi-particle. That's all it is. They call it a particle. That behavior, that collective behavior is called a particle. And there you see an example at the bottom. Just one example, by the way. I've shown others the other day, so you can check on the previous videos. You'll find some other examples. Okay, and from that, they came up with all these list of quasi-particles that, to this day, all the mechanics of quantum everywhere in the world. This is what they do. This is what they do for a living. They study quasi-particles. They've forgotten about the standard particles, about the atom. They learned that in kindergarten physics when they're getting their masters. That's kindergarten physics. You know what a proton is, what an electron is, what a muon is, a pion. They left that stuff behind. Now they've evolved, and now they talk about what? Quasies. They're into the quasi world. Why? Because they get a job somewhere, and usually they get a job in a manufacturing place, either as an engineer or to study or to develop or some product. And so they go in there and they try to study behavior. Collective behavior of particles, okay? And so they gave names to all these behaviors because this guy studies this thing, this other guy studies that other thing. And what happens out of this, they had to give them names so that they could put them in their writings. They publish papers and they said, well, what are we going to call this? Well, we'll call this quasi-particle this. And the other guy says, I'll call it that. Okay, and so they have all these different names for these different quasars, okay, or quasies. And here's a list of them, okay? There's probably more of these out there. I'm mentioning probably 90% of them, probably, and again, I must have missed a couple here and there. This is what the standard model of quasies looks like. Okay, you've got all these so-called particles, and what they are, they're all collective excitations of something. Okay, in fact, look at the last one, the wrinklon. It's got to do with wrinkles. Okay, and you'll see some of them, like the orbiton there, it's got to do with orbiton. You got the oscillon, it's got to do with oscillations, okay? What other one can we mention real quickly here? Perhaps the plasmon, got to do with plasma, okay? So these are the particles that these people study, and they're not really particles, they're collective excitations that they go into the lab, they can't see or touch what they're analyzing. And so they theorize about it, but then they introduce the word proof and exist and evidence. They introduce these words because they say, we've proven it, we found, we discovered. Because they got to get their Nobel or their Wolf Prize or whatever prize out there, and they say, look, we did something for humanity. We discovered this particle. Well, did you discover like a particle, like a little bead, a little grain of sand? No, it's not even close, because we're not even talking about a quantum particle that's in the standard model. We're not talking about a little ball, which is not a ball even there, in that case. They're talking about an excitation of many particles. And that's what all these particles are. Excitations of many particles. And let me go through some of these, just so that you get a feeling. Okay, I'm not going to go through all of them, by the way. I don't want to bore you to death, but I want you to get the hang of what these people are up to, what you're paying for, because these people rely on government funds in almost all cases, either directly or indirectly. They depend on grants, and also on rich people contributing to their specific pet projects. Okay? So there's a lot of money going into this research into quasies. Okay? And here's I'll just review real quickly here. This is the phonon I presented the other day, and there's several types of phonons. You can see there, each one of these vibrations is a different phonon. So you got work there, job security for lots of so-called physicists, mathematical physicists, who study each one of these different types of vibrations. Okay, and those are the phonons. Those are people who specialize in phonons. Okay, I mentioned this. This is probably an even more important field, which is the holes. Okay, and I showed this the other day, where you have the holes going in to the negative pole or negative terminal of a battery. Why? Because the electrons, the negative electrons, are going in the opposite direction, leaving a hole in the valence band of the atom, and that movement of the hole opposite of the electron bead, that's flow, is considered a positive current. Okay, so that's how this came about. And again, this is important in the semiconductor business, which I worked on quite a bit, because of this. Because what happens when you put a p-type and an n-type crystal together, they form what is known as a depletion layer, and the electrons allegedly go through the barrier and neutralize those atoms. Okay? So it creates this neutral region known as a depletion region. And so this is important in semiconductors, and it's one of the things I want to mention today, and that's got to do with the fact that all these so-called quasies, they have to do, not with science, they have to do with technology. Okay? That's why they're important, because, people don't care if you understand the invisible world out there. They don't care if you can explain it in a rational manner. That's out the door. They don't even care about that anymore. What they say, this is how we're going to explain it, but that's not important. The important thing is to discover the behavior, whatever behavior you're studying, giving it a name, always ending in on, okay? On's got to be on to be a particle, okay? And you give it a name, and you study it, and you use it for something. You don't understand it any more than Edison understood electricity, what electricity is. He didn't need to know that. He just needed to develop the filament for the light bulb. And so, because he was working on developing a gadget. So he doesn't need to know what electricity is or how to explain it or anything like that. He didn't need to have a physical interpretation for electricity. What he needed was to develop a gadget. And so they said, well, you send electricity here, you produce this effect, and it creates light. And that's what we need to sell out there to the people and make our company and the investors richer. That's all it was about. And this is no different. These are people who are studying semiconductors in the case of holes, right? And what they do, they study the semiconductor, but they don't understand what's happening there in real life. They simulate it always with particles, because that's the easiest thing to put an equation to. You can describe it with an equation much better if you've got a particle than, for example, an extended entity like we're proposing, such as a rope. Okay? So that's how the particle keeps having an everlasting life. It never dies, because it's easy for the mathematicians to deal with particles, because they can put a value, for the point particle, for whatever value it's got, they can put that in the equation. Okay? So this is the issue. They don't understand it, but they don't care if they don't understand it or not. The important thing is, can you develop a gadget that makes us money? That's what it's about. Okay, so let's go through a couple of these. Here's the anyon, okay? And just go alphabetically through a couple of these just so you get the hang of it. What is this? Is it some kind of bean? Is it some kind of grain of sand? A little pearl of some kind? No, it's a type of quasi, right, that occurs only in two-dimensional systems. Two-dimensional system? What the hell? I thought two-dimensional was outlawed in our real world. And these people say the anyon only belongs to two-dimensional systems, which is going to give you an idea that they're talking about maybe geometry, for sure mathematics, for sure, guaranteed, not physics. In a two-dimensional world, two identical anyons change their wave function. They change their wave functions. Like if a wave function is something you change, you trade or you exchange or throw away or a kick or a jump or whatever. When they swap places in ways that can't happen in three-dimensional physics. Okay? So now we move from three-dimensional physics to two-dimensional physics. They are going to use this anyon. This process of circling one particle around another is referred to by its mathematical name as braiding. Okay, they call it braiding. Okay, so these things are going to twist around each other. Sounds like this, like a rope. Braiding, maybe. Okay. Braiding encodes information in a more robust way than other potential quantum computing technologies. So what does this have to do with science? No, it's got to do with technology. with gadgets, with inventing stuff. Okay? Not a billion anyons were detected by 2 experiments in 2020. Did they detect a particle? No, they detected a behavior, a collective behavior of many particles, and they call that whole behavior, which is more or less localized because they're talking about a microscopic world, and they say, oh, it behaved in this way, we're going to call that what? An anyon. Okay? And not a billion anyons have not been definitely detected, although this is an active area of research. Okay, so this is what you're paying for. You're paying for these people to do research and development on 2-dimensionals things, non-physical, okay? So that means they're just going to describe it mathematically. And what for? For technology, not for science at all. It has nothing at all to do with science or physics, but it's included within mathematical physics, and it's a very strong area of research, okay? Okay, let's continue here with the next one on the list. Again, I'm just going to go alphabetically through a couple of these just so you get the hang of it. This is the bion. Nothing to do with sex, okay, just because it's got the prefix bi in there. The bound state of 2 solitons. You remember what a soliton was? It was a wave, okay? Somehow it became a particle. And they take 2 solitons, okay, and they say if these 2 have a bound state, they're kind of interlocked, you know, maybe entanglement. One soliton somehow affects another one from a distance. We don't know how or why. We don't care because we're just doing technology, right? Or in systems where the bound state periodically oscillates. A breather. Okay, what's a breather? A nonlinear wave. Somehow the particle converted into wave, wave goes to particle. That duality, okay, that comes in handy. Okay, annoying for them because you'll never find a wave in the standard model, in which energy concentrates in a localized and oscillatory fashion. There it is, in a nutshell. Then we have the bipolaron type of quasi. Okay, quasi consisting of 2 polarons. You don't have one, you have 2. Okay, so what's a polaron? Well, it's a quasi used in condensed matter physics to understand the interactions between electrons and atoms in a solid material. Okay, so we're talking about interactions here. They call that a polaron, then they take 2 polarons, which is 2 interactions, and they're going to have a what is called a bound state, which is essentially action at a distance entanglement. That's essentially what they're talking about. Between particles, no, not really particles. They're between electrons, but they're not talking about an electron anymore, or a positron or anything like that, a discrete particle, which is not a particle to begin with, but they're talking about the excitations of many of these particles. So they have a bunch of excitations here, which is a wave. We have a bunch of excitations over here, which might be a field or a wave, who knows what it is. And if they're kind of bound to each other, entangled, action at a distance, sort of, this one affects that one, who knows how, by magic, then they're going to call that a bipolaron. Okay, so this is how it goes. And what does a polaron do? Well, it describes an electron moving in a dielectric crystal. I mean, we're not talking about an electron, we're talking about the motion of an electron now, okay? Okay, let's look at another one here, okay? Just going down for a couple of these so you get the hang of it. That's all I'm doing here. And they invent these strange names. Let's see if I can pronounce this thing. Bogoliubon. Bogoliubon, okay? It's a quasi that occurs in superconductors. What are we talking about? Are we talking about science, physics? No, we're talking about technology, gadgets, things, inventions, okay? Where superconductivity is characterized by a condensation of Cooper pairs, which you see at the bottom there, in the same ground quantum state. Bogoliubov, because it's got both names, Bogoliubon and Bogoliubov. I think it was because it was a Russian who invented this stuff. Quasars, or quasis, are elementary excitations. That's what they are. Above the ground state, okay, like an excited state of an atom, that you have the ground state and you have the excited state, and this is above the ground state, okay, which are superpositions, okay, of the excitations of negatively charged electrons and positively charged electron holes. Not positrons. These are holes, which are the absence of electrons. Because they have the absence of electrons, they're going to call that positive, and they're going to have superpositions of these vibrations, excitations. I mean, I lost track by now, you know what they're talking about. And they're going to call these Cooper pairs, and this is what they're going to use the bogoliubon for. They're going to say it's a quasi-particle. It's an excitation of elementary. It's an excitation of elementary excitation. That's what it is. It's pure excitation, excitement all around. That's all this stuff is. What's a Cooper pair? A pair of electrons bound together at low temperatures. So they're going to take these electrons, they're going to freeze these things. They're going to see what kind of vibrations they have. They're going to look at the holes that are vibrating, vibration of holes, which is the absence of an electron, which is, again, you take the electron out of the valence band and somehow something remains vibrating in there. And it's not localized, it's just a bunch of vibrations of nothings, of the absence of electrons. That's what the bogoliubon has to do with. That's what you're paying for. I might need a beer after this just to get my sanity back, okay? Well, if you ever wanted to ask, here it is. I finally found it for you. Okay, here's the answer. You always wanted to know what a configuron was, right? You know what a configuron was. It's elementary configurational excitation, another excitement, okay? In an amorphous material technology, which involves breaking of a chemical bond. Okay, so we have a breaking of a chemical bond and creates some kind of excitation, and that elementary configurational, excitation, that's going to be called a configuron. That whole thing turns into a particle. Now, what sense can that possibly make in science and physics in trying to understand how this universe works? Absolutely none. Okay, and then we have the dislon. Obviously, we learned this in kindergarten, right? Localized collective excitation, another excitation, bunch of excitation associated with what? Dislocation in crystalline solids. Okay, so you have a dislocation, something out of place, and we'll call that a dislon. Okay, what's a fracton? Well, that's a subdimensional particle. You know, you have dimensions, and this is like a quarter of a dimension. What's a dimension? Dimension is direction and orthogonality. That's what a dimension is. Okay, 3-dimension, you say the table is 3-dimensional. What do you mean? It's got length, width, and height. And these guys partition the dimension. They cut it in half. They cut direction in half. They have half a direction, maybe a quarter of direction. So they call it a fractal or a fraction of a dimension. That's what a fracton is. It's an emergent topological quasi crazy excitation. They're all excitations. They get excited about these things. A collective quantized vibration or excitation or movement, jumping around back and forth. Okay, that's what it is. Oscillation, which is immobile when in isolation. So the only way it can move, vibrate, is when you put it with its buddies. When it's isolated, the fracton doesn't move. It doesn't vibrate. There's no excitement. Fracton has no excitement when it's alone. Now, don't forget the very important holon, okay? Also known as a charge-on. Why? Because it comes from hole and charge, right? One of 3 quasies, along with spinons and orbitons, okay? Those are very important particles, okay? You gotta have them for the test on Friday, okay? That electrons in solids are able to split into during the process of spin-charge separation. They're gonna take the spin away from the charge, if that makes any sense to you. Here we have 2 concepts that belong, for example, to an electron top. The top is spinning, and we're going to take the charge over here and the spin over there because they part company. Okay? Whatever that means in mathematics. When extremely tightly confined at temperatures close to absolute zero. Yeah, they're studying a lot of this stuff, what happens to materials at very low temperatures. Because they want to see if they can develop these, supercomputers, as they call them, or quantum computers. And what they're going to be doing is they're going to freeze them. They're going to bring them down to very low temperatures to see what kind of effects they have. They have maybe less resistance, maybe not as much heat in the little chip, so they can make them smaller. See, one of the problems you have with semiconductors, the smaller you make them, the geometries are closer together. And so they heat up. And you can't make them any smaller because they heat up even more and more and more, and finally they melt. But what if you were to cool them down and freeze them? Well, then you can get into this quantum computing, this super cool world. Okay, that's what it's all about. It's about developing technologies. Do they understand what's happening in that invisible world? Absolutely not. They simulate it with particles because that's where they can apply their equation. They can put that number in an equation. But then they're not interested in the physical interpretation. All they're interested in is what effect does it have, and can I use it for something? Can I make something out of it? Can I invent something? Can I make money? That's what it's all about. That's why there's investment in that world. That's why so many of these so-called physicists, mathematical physicists, mathematicians is even a better one because they do all their explanations are magical, and they claim at the end of the show that they don't understand, the quantum world. Of course not. Not if you're going to simulate it with particles. You'll never understand it because there are no such things as discrete particles. You would not be able to explain action at a distance with particles, much less can you explain them with quasies, because quasies are localized vibrations of many particles, which they turn into a single particle, and they call that a quasi. Quasi this, quasi that. They're all quasi. Okay, here's maybe one of the last ones I'll mention here. Okay, this is the exciton. Okay, how's that for a particle name? I mean, if they're all excitations, I'm sure the exciton has to be the number one particle. You know, what is it? It's a bound state of an electron and an electron hole. So these things are bound. When you hear the word bound, it doesn't mean bound. Like nothing in mathematical physics is what the word says. Spin is not spin, particle is not particle, and bound is not bound. Bound does not mean that it's tied like, by a string or a wire or a cable. That's not what bound means. Bound means that action at a distance by magic. That's what bound means. Bound means entanglement. This particle does something, this one follows suit and imitates it or acts in the opposite direction or whatever. In other words, it responds to this one through magic, only through magic. Magic wand, okay? It's done through magic. It's called black magic. They don't understand it, they just say it does so. We've proven it. Here's the equation, and we saw it we observed it in the lab. Did they observe whatever happened in between, the mechanism? Absolutely not. They cannot explain that at all. Okay, so it's important to understand that. Okay, it says an exciton form when material absorbs a photon of higher energy than its band gap, and so on. Well, you can read that later on. Again, all these quasies, they have nothing to do with science, because you cannot explain any phenomenon of nature, any invisible phenomenon of nature, just by saying that it's an excitation of many particles. Okay, I do want to mention one last one, only just to rub it in. Okay, here it is. I think it's this one. Yeah, this is called a dropleton, which are droplets of electrons and holes. Why do I mention this one? Well, I mention it because I just want to show that this is a formal paper written on these dropletons. And what these people are saying, as you can read it here, is that it's got to do solely with technology. And let me just read here what's in that red box there. Building blocks for more complicated structures, it is often possible to incorporate interactions in theoretical treatments of crystalline solids by introducing suitable quasi-particles that have an effective mass, spin, or charge, which in turn affects the material's conductivity. That's what they're interested in. Optical response or phase transitions. Additional quasi-particles interactions may also create strongly correlated configurations yielding new macroscopic phenomena. In other words, they're interested in the phenomena, in the behavior. They're not interested in the explanation. Such as the emergence of a mod insulator superconductivity or the pseudo-gap phase of high-temperature superconductors. In other words, they're interested in technology. But see, the interesting part is that they mention the exciton, the bi-excitons, and the poly-excitons. And they talk about the existence of these particles as if taken for granted. Of course, they never define the word exist in physics, so we don't know what they're talking about when they say exist. But look on the right-hand side there, the box in red again. It said, we present experimental and theoretical what? Evidence for the existence of quantum droplets in an electron hole plasma. So these people are claiming that they've proven the existence and they present evidence, which is what mathematical physics is all about persuading your colleagues that you found it, that you discovered it, so that you get some kind of prize of recognition or whatever. And that's what it's all about. It's like saying, we saw something in the lab. What did you see? Well, we saw, what was it, a dropleton? What do you mean you saw a dropleton? What is a dropleton? What's a... Okay, yeah, I understood that. And what are they talking about? They're talking about a behavior, collective behavior. And why is it important? Well, it's the only relevance of it is in terms of physics, of technology. That's all they're interested in. They're interested in technology, and if you can develop some kind of gadget with it, or make something more efficient, or you can run it maybe at colder temperatures, or faster, or longer life, or any of those things that you can improve on an existing device, or gadget, or whatever, then for them it's worth a lot, because that translates into money. It's part of the research and development of a lot of companies. So there's no problem there. I just want you to understand that it's got nothing to do with physics. Physics is about explaining, about understanding what's going on in that secret world. If you're going to dismiss the explanation, the physical interpretation, say, I described it, I saw it, I observed it, I called it, I gave it a name, fancy name, Okay, yeah, and it does this, and it's going to save so much money, or it's going to create a faster device that we can sell much better than the competition, and so it's going to earn the company money. But yeah, all that's got to do with business, with with developing, research and development, with manufacturing, that sort of thing. It's got nothing to do with explaining how Mother Nature runs her shop. It doesn't explain anything about electricity. It doesn't explain anything whatsoever about how magnetism works, how gravity works, how light works, how the atom works. That's where it fails. And that's where it's misleading, because a lot of people say, well, what do you mean the mathematicians don't understand, that they cannot explain, that they don't understand quantum mechanics? We wouldn't have all this technology if they didn't understand. Well, no, it's because experiment and technology have nothing to do with science. You can do an experiment. What's the purpose of the experiment? Either to reinforce your preconceived beliefs, notions, or that of others. An experiment is used to convince people. It's used to persuade. That's the only purpose of an experiment. It's that you satisfy yourself that whatever theory you have in your mind, you confirmed it with that experiment. And you haven't convinced everybody else, but then you go to the court and you show it to the jurors, and you say, look, here's an experiment that proves my theory. Proves. And I proved the existence of the plasmon or the bion or any of those particles there. Bipolaron. I proved the existence because, look, here it is. And see, you see that vibration? That's the polaron. That's how it works. An experiment is only used to persuade people. I mean, you can run any experiment you want at home. When you come to the conference, we need for you to explain what you understood or how it works. You need to explain the mechanism. If you're just going to tell me a description, say, yeah, a chair has 4 legs, well, that's not much of a science, And this is what these people are doing. They say, we observed. What did you observe? Well, we observed these vibrations, these oscillations, these excitations. And we gave it a name. We called it the bipolaron, or the phonon. Oh, okay. And what does the phonon do? Well, it makes you a lot of money. Oh, okay, then I like it. That's what it's all about. Where's the explanation for what's happening in that secret world, in that invisible world? For that, you need a mechanism, and for mechanism, you need what? You need objects. You need to do them with things. For that, you need to know what a thing is. Okay. Anyways, this is what I'm proposing. Okay. I took the trouble to put them, like Mendeleev did with the standard, with a model of chemical elements. Okay. And I did something similar with the quasies, and I put them there so that I hope I get credit for this, somewhere. And while I was doing this, I did my own research. And don't laugh at me, but it took me a whole week. I was watching day after day without sleep, okay, without eating almost. And I was watching my curtain. I got disconnected there for a second. I think I'm coming back. Okay, I'm reconnected. Anyways, I was watching my curtain for a whole week, okay? And this is what I saw. I found an excitation one day. And because of that, I call this excitation, this collective excitation of the cloth, and I called it a phantom. But, because of the rules, the laws of quantum mechanics, I had to change the name to a phantom, because everything has to end in the letter N. Okay, so there you have the phantom. That's my contribution to the quasies. Okay, and all the others are there in nice, neat fashion so that you can locate them. They don't belong to the standard model of elementary particles. They belong to the standard model of quasies. Okay, so I hope I get credit for that. Okay. Anyways, here's my conclusions on the quasies. Okay, you can take this to the bank. Okay, quasies are not particles. They're not corpuscles in any sense of the word at all. Why they use the word particle to mislead you, I have no idea. Maybe it's just for that, just to mislead you to think that they're doing physics when they're not. Okay, they were invented for what? For inventions. So they have an invention for an invention. What's the point of it? Technology, making money. That's all it is. Its interest is only in the application for gadgets, for devices. Making something faster, run at colder temperatures, maybe longer lasting. A lot of reasons for these things, but it has to do with looking or discovering behaviors that were not seen before. And usually they do those at very low temperatures. Okay, so they run something, they can't see in there, they don't know what's going on. They simulate it with particles and they say, well, we'll call this particle A, now particle B. Sorry, I meant quasi-particle A, quasi-particle B. Physical interpretations made with quasies, they're all crazy. They're all irrational. Not one of them is rational. You can't simulate any invisible, intangible phenomena of nature with any kind of particle, let alone with quasies, okay? And you can't even do it with classical particles. You know, the people who use the ether, which is a bunch of particles out there, they simulate everything with vibrations of lots of particles. They call those waves, transverse waves, longitudinal waves, and so on. It's all done with particles, discrete particles. And you cannot explain anything with discrete particles because the big problem that particles and waves, which are made of particles, will never be able to explain is action at a distance. You cannot explain gravity. You can explain how this particle over there pulls, the word pull. You cannot explain how a particle pulls on another. And so you'll never find the word pull in any simulation with particles, ether, Dirac sea, whatever you want to call it, space-time, made of points, events. All those discrete particles, you'll never explain a single invisible, intangible phenomena of Mother Nature's.